This is a time-of-flight or distance sensor, commonly used in industrial applications as an input device for simple object detection. This device works by emitting a laser and identifying how long it takes for the light from the laser to bounce back from an object to the sensor. This sensor has a few cool features such as a variety of mounting methods, rotatable connector head, onboard programming buttons, and reliable sensing with reflective materials, a common issue for laser-based sensors. Taking a look inside, we can see a lot of adhesive, which is common when companies rate their products to an IP rating. This one in particular has IP67 rating, meaning it's dustproof and can withstand being submerged in water for a short period of time. Inside, you start by seeing a gold casing. This casing is typically seen around sensitive sensors and acts as both EMI and RFI shielding, which stands for electromagnetic interference and radio frequency interference. Without this casing, sensors can pick up noise from other sources, which can lead to erroneous data. To minimize this noise, the shielding is incorporated around the equipment to block the noise, just like how closing your windows can silence a noisy neighbor. Here you can clearly see how that rotating connector works, and we'll take a deeper look into that in a second. As I pry out the brains to this sensor, I'm peeling off the back half with additional adhesive on it. These sensors are designed to be able to take a fall and hit without losing that IP67 rating, and the adhesive ensures that the sensors don't shift inside. Unfortunately, disassembling the sensor is particularly a destructive process, so this isn't going to hold up the IP67 rating afterwards. Here you can clearly see that the gold EMI and RFI shielding completely encapsulates the PCB and the brains to this sensor. As I disconnect the connector to the PCB, you can see now a bit clearer on how this connector is held in place with a retaining clip. Removing the retaining clip allows me to remove the connector fairly easily. With the connector removed, we can see a few design features. Firstly, there's an O-ring, which is typically installed to ensure proper sealing and ensuring that there's no leakage into the sensor. Additionally, we see the groove that was set for the retaining clip. If you look closely at the connector, you'll see that there's a small indent, which is the main feature as to how the connector was not able to rotate continuously. Next, let's take a look at the brains of this sensor. To achieve a compact design, there's a combination of double-sided PCBs and a ribbon cable to integrate the PCBs together. 4 screws mechanically hold this sensor together. However, as you saw previously, there are more points where the shielding is grounded to the PCB. Grounding ensures EMI and RFI is captured and dissipated. Taking apart the two halves, it looks like the shielding also serves as a partial heatsink to distribute heat generated from the laser. Here we can see all the internal shielding components together that encapsulate the sensor. An additional component to shielding is this red filter, used for infrared filtering or bandpass filtering. This allows only a specific band of light to enter and blocks unwanted light, ensuring the sensor only reads back its own IR pulses. The top circle here is where the emitter is housed, and the bottom half is the receiver. You can see that the convex lens sits on top of the receiver, focusing light towards the sensor. This allows light to be received from a much larger surface area than just the receiver. This in turn, however, produces light at a focus point, hence why the thermal pad is necessary for heat dissipation. Finally, this sensor uses a clever method to cancel out ambient light. The small bifocal on the lens is key. It's designed to isolate and measure only the surrounding infrared light, treating it as background noise. The main part of the lens captures both this laser's signal and this noise. The sensor's electronics then subtract the background noise from the main reading. This process leaves a clean, accurate measurement of the laser's reflection and provides a reliability in a wide variety of environments.